So let's move to the, why is it not moving? I think I have to click it. Yeah, so most of you already know the neutrino story of IceCube, how neutrino detection happens. So I'll just briefly introduce you to how cosmic ray detection happens. So whenever, like from an astrophysical source, a cosmic ray primary interacts with particles in the atmosphere and we see an air shower. So such an air shower then propagates to the isotope surface array. We see some signal footprint on the surface array, and this is primarily due to the electromagnetic component of the air shower and some low energy muons. Whereas the high energy TeV muons can also propagate deep further in ice, and we also see some nice footprint there. And obviously, working with isotope and in-ice together provide us a unique three-dimensional detector, which is not possible in most of the other detectors. And just some really nice photos of isotope tanks on the right, and then PMTs inside and the in-ice hole. These were some nice animations, but okay, anyway. So let's move to the previous result. So about 3 years ago, IceCube published the spectrum and composition analysis. So where what we did was we had some high-level reconstructed features, and that was an input to a simple neural network, and we predicted energy and mass. A little bit detail about the features. So we had S125, which is a shower size parameter, and it's mostly an energy proxy. Then zenith is obviously the directional information which we need, and the rest of the three parameters are information from NICE primarily. And since I told you it's mostly TeV muon, so it's in some way trying to capture the either the muon deposit or the muon number. So for energy estimation, this work was really good. However, for mass, we still had some way to improve. So what we did for the mass estimate in this analysis was, in each energy bin, we performed some kernel density fit, and in each energy bin, we could provide a average LNA, average mass. Moreover, if you, I don't know if you can see the error bars, or okay, you can see the standard ones. So there were huge error bars, and we did not have a consistent model which satisfied for all the primary types. So obviously, we want to improve this. And as I told, my talk is divided into two sections. So the first one is obviously, move beyond the these features and try to use some low-level information. So try to use a full footprint, and that's what the first one is. And the motivations are obvious. We would obviously want to benefit from the detailed information of low-level signal information, where we have the iStop LDF and the INICE LDF. And like this, in principle, just trying to capture high-energy muon deposits with the electromagnetic deposits. By the way, there is also another really nice talk by IceCube by Steph on July 28th, where he'll discuss more about muon number estimation. So I also recommend you to listen to that. So when I use the full signal footprint, I would obviously want to reduce dependence on some prior reconstructions. I would also want faster inference or real data. And the current method which allows that is obviously jumping into deep learning methods. So at IceCube, we have a current implementation of a CNN. So CNN stands for convolutional neural network, where Mirko Hohenfeld has done a really nice work in the neutrino sector. So where what we do is we map our hexagonal detector to orthogonal geometry, which is necessary for most of the CNN architectures. And then he uses these for some reconstruction for the neutrino sector. However, if I would have to choose a safe path, I would have easily chosen CNN. But what I wanted to do with my analysis was make it flexible for the detector upgrade. So in future, we'll move from this hexagonal geometry, which can be easily mapped to orthogonal, to a more irregular geometry. We are upgrading to Gen 2 optical. Alina discussed this yesterday. We are also adding IceCube upgrade, which is in the central part. And whatever, what in total this will do is shift us from a regular geometry to a more irregular one. Moreover, we are adding even more complex detectors. We are adding scintillators, radio antennas. This will shift the geometry even more irregular. our DOMs, which are like PM trees plus some electronics, are getting more complex. So in total, continuing with CNN will be a difficult choice because we would not be easily able to map it to orthogonal geometry or come up with complex kernel which are necessary for the method to work. So the obvious choice was then to move towards graph neural networks. And in simple definition, you can just replace the pixels, which are like the dots here in CNN by something called nodes. So you can just map the DOMs as nodes. And then the connections are defined by some prior you set. So how does it happen for IceCube? So what I do is I take the iStuff footprint as well as NICE footprint and then perform some spatiotemporal cleaning around the pulse track. Obviously here I need some prior reconstruction of the track, but in future work, I'll obviously try to move beyond this. And then what we do is we interpret the DOMs, which are basically the small circles here, as the nodes of the graph. And the node features are some spatiotemporal measurements like charge, where was the particular DOM in the detector which was hit. And then we generate the edges, which are also important for graph neural networks, just to share information among the detectors or the nodes. And these are some weighted KNN connections. So to each node, I connect some k neighbors, which becomes the hyperparameter for a network. And these are weighted by their spatial separation. So if the detectors are close, they're given higher weight. And then you get a graph like this. This becomes the input for the neural network, whatever the complex architecture is here. And then finally, the primary mass prediction is done. In addition to this, we also have some pre-engineered features. Some of the pre-engineered feature I already discussed on the first slide, like shower size and the few others. In addition to that, as I mentioned, I also have some new one. These are just some other feature details. I won't go into detail. So these are the two new ones. Just remember the names for now. So impact weighted charge and ratio parameter. All the other ones are like published in some of our IceCube previous works. Coming quickly to the architecture. So for a second, ignore the central part. What's unique about this architecture is we are moving beyond performing a simple classification, like basically telling it if it's proton, iron, or helium or something, or just telling LNA to doing both of them together. So rather than having a LNA prediction at last, we perform classification as well as regression together. And what this thing provides us is an extra point estimate of each event, which was earlier done by some kernel density fit, which is obviously now then dependent on the data set you perform the fit on. Coming quickly to the architecture details. So this is some random example which I chose. So, and the small blue dots, I don't know if you can see, these represent the signal at the particular station or particular tank, and the edges are the graph edges. And the first capture of information is some input signal global statistics. So this is a measure called homophily, which basically measures how homogeneous your signal is. So if there are more muons in a shower, we expect more stochastic deposit in ice. So there we would expect the homophily to be low. And then it's a standard convolutional pooling layer, which is also the case for CNNs. There are three different types. I won't go into details, but these either try to capture some structural information or try to capture, okay, which DOM is more important than the other one. And these are finally then concatenated with the pre-engineered features to finally input into a standard fully connected, and this is trained together. Coming quickly to the results. So here I have compared my results, which are the graph-based results, with RF-based methods. So RF-based is a random forest-based method. So this is a work done by Matthias in our collaboration. This is published here, and it's a slight improvement over the baseline. On the y-axis, okay, thank you. On the y-axis, you see the mass prediction bias, and as you can see over the whole energy range, we see an improvement in the bias for all energy bands. And I'm also trying to improve the precision a bit more. Let's quickly jump to the second part, which is pre-engineered features. So the first one, as I told, is called impact weighted charge. So what I do is divide the in-ice track into 5 percentile bins, and then in each bin I calculate some impact weighted charge. And impact here just means the perpendicular distance. And why do I do that? The motivation is simple, that at same energy we expect a wider muon bundles from for iron than proton. And the simple motivation is iron shower interacts early in the atmosphere, which I think you also remember from XMAX discussions earlier. And they also have larger muon multiplicity, so larger transversal momenta in principle, and that's why in the combined effect we expect wider muon bundles. Just coming quickly to how it can be seen. So this here I've shown for the bottom of the shower, so the last percentile bin. In principle, you can also do it for the other percentile bins. And you can see again, C for all energy bin, which is x-axis. Here I've replaced it by S495, which is again energy proxy. We see a good separation between proton and iron. So it seems like a good compression sensitive parameter, and this can also be seen by the figure of merit plot on the top. And as I told, this can also be done for all the other percentile bins, and this can in future also help us understand shower attenuation and possibly help understanding photon propagation in ice. Coming quickly to the second one, which is the ratio parameter. So this is a work which was motivated by Cascade Grande. So Cascade Grande, for those who don't know, was an experiment at KIT only, so pretty close to home. And what they observed in there was the ratio of muon to electron is a good compression sensitive parameter. This is just one of the famous plots from their publication. However, what we lack in IceCube is the ability to separately measure muons and electrons. So just as a quick check, I use some proxy parameters for these. And the quick results from this, so again, as you can see by the plot on the right, we see a really nice separation between proton and iron for over the whole energy range. And if you can see by the figure of merit, it becomes better and better as you go higher in energy. And this again shows the potential of just rough estimates of electron number and muon estimate. And as I told you before, Steph will go into more detail how we can estimate these better. So in total, the outlook for the talk is, okay, I obviously need to fine tune my network a bit more, perform hadronic interaction model comparisons, compare it with data. And just for conclusion, I think we are leading in a good direction for improving cosmic recomposition analysis at IceCube.